All right, so get this. You know how everyone's so excited about quantum computers and all their potential?
Yeah.
Well, it turns out that one of the most important things that makes them work,
Right.
quantum entanglement,
Yeah.
is way more fragile than we thought.
Uh-huh.
So today we're gonna look at this new discovery that kind of throws a wrench into things.
Oh.
Turns out that heat can actually destroy entanglement.
Wow.
Yeah, you heard that right. And this isn't just like some theoretical thing. It has some big implications for building these super powerful quantum computers.
For sure. What's really interesting is that this forces us to kind of rethink how we think about these quantum systems,
Yeah.
especially at high temperatures.
Okay.
So we're going to dive into why that matters.
Okay.
Not just for quantum computers, but maybe even like how the universe works at like a really basic level.
Okay, so entanglement, we're talking about spooky action at a distance, right?
Yeah.
Two particles linked together
Right.
in this way that even Einstein thought was mind-boggling.
Yeah.
We know it's super important for quantum computing to work its magic.
It's essential.
Yeah.
Right? Entanglement is like the foundation for all these quantum algorithms that people are proposing.
Okay.
It's what lets quantum computers tackle problems in ways that normal computers just can't even touch.
Right.
And it's not just computing either. Entanglement is part of other quantum stuff too, like superconductivity.
Okay, so, but now we're finding out that heat can just like wipe it out.
Pretty much.
Yeah.
And it's not like a gradual fading either.
Yeah.
Researchers found there's a certain temperature.
Oh, wow.
Above that, entanglement just disappears. Poof, gone.
Wow.
Yeah, some early experiments kind of hinted at this, but this new research gives us like a solid mathematical proof.
Okay.
Yeah.
And here's where the story gets interesting. The researchers who figured this out weren't even physicists?
Yeah, you're right.
What?
They were computer scientists working on a new quantum algorithm.
Oh, wow.
Yeah. Their initial goal was to find a faster way to simulate quantum systems, specifically at higher temperatures.
Oh, that's ironic. I know, right?
So they were trying to build better tools for quantum computing,
Yeah.
and they stumbled on this like fundamental limitation.
Exactly. What's even more interesting is that their proof came from a computer science perspective,
Oh.
not a traditional physics one.
Wow. Yeah. Okay.
Yeah. Yeah, it really shows how connected all these different areas of science can be, you know?
Yeah.
Sometimes breakthroughs come from the most random places.
Yeah, for sure. Okay, so walk me through this.
You okay?
How did they actually discover this thing?
Yeah.
What were these computer scientists even working on?
So they were working on something called the thermal equilibrium problem.
Okay.
So imagine you've got like all these atoms at a certain temperature,
Uh-huh.
and over time they like settle down into a stable state, like their resting state,
Right.
called the thermal equilibrium state.
Okay.
And that determines a lot of the system's properties.
So figuring out this resting state is key to understanding how these quantum systems behave at different temperatures.
Yeah, exactly right.
Okay. Now here's the thing. The difficulty of actually calculating that state
Okay.
changes like a lot with temperature.
Really?
So at really high temperatures, you can use normal algorithms like the kind we use on regular computers to get a pretty good approximation.
Right.
But as the temperature drops and quantum effects become more important,
Okay.
those normal methods, they just don't work as well.
Yeah, because things get too complicated.
Yeah, exactly.
Yeah.
And for some systems at like super low temperatures,
Yeah.
even quantum computers would have a hard time figuring out that equilibrium state quickly.
Wow.
The hard part is like that exact point where normal algorithms stop working
Right.
and quantum algorithms become necessary. It's kind of a gray area.
Okay. And that's where these computer scientists come in.
Yeah.
They were trying to come up with a quantum algorithm that could tackle this
Right?
in that gray area at lower temperatures,
Yeah.
where quantum effects are really strong.
Exactly.
Hmm.
They were specifically interested in a range of kind of high temperatures where people thought there might be these fast quantum algorithms,
Uh-huh.
but nobody had been able to prove it.
Right.
They thought they could make a faster algorithm by using a trick from something called learning theory,
Oh.
which is this area of computer science that deals with like statistical analysis.
Okay.
They did come up with a new algorithm,
Uh-huh.
but
But there's a twist, right?
oh yeah, just as they were about to publish their results,
Mm-hmm.
another group of researchers published like a super similar algorithm.
Oh, no, they got stooped.
Yeah, they did.
Ouch. That's gotta hurt.
Yeah, but hold on.
Okay.
If their algorithm was pretty much the same,
Yeah.
how did they end up proving this big thing about entanglement and heat?
Right. Yeah.
That's the amazing part.
Okay.
They were looking at their work next to the other team's findings,
Uh-huh.
and they talked about their approach with a physicist
Oh.
from the other research group.
I bet that physicist was pretty surprised.
Yeah, totally. He realized that these computer scientists
Yeah.
had proven something crazy, like by accident,
What?
in one of the steps of their algorithm.
Wow.
They had actually shown that in any system with spins,
Okay.
at thermal equilibrium,
Huh?
entanglement just vanishes above a certain temperature.
So they were trying to make quantum computing better,
Yeah,
and they stumbled on this like fundamental limit of the quantum world.
exactly.
Yeah.
It's wild how scientific discoveries can happen in the most unexpected ways.
Yeah, so they proved that heat kills entanglement.
Yeah.
But physicists kind of already suspected this, right?
Yeah, you're right. There were some hints before.
Okay.
But those studies, they couldn't actually measure entanglement disappearing.
Right.
And they mostly looked at small systems, which aren't that helpful for real-world applications.
So there was always that question of like,
Right.
could entanglement still exist
Yeah.
at higher temperatures and larger systems?
Exactly. And the previous theoretical limit on entanglement didn't rule that out.
Right.
It suggested that the temperature where entanglement vanishes might depend on the number of atoms in the system,
Mm-hmm.
but this new research completely closes that door.
So they proved that no matter how big the system,
Right.
entanglement has a hard limit when it comes to heat.
Exactly.
Yeah.
They showed that the critical temperature where entanglement disappears only depends on
Wow.
how strongly nearby atoms interact, not on the total number of atoms.
Oh, okay.
And it links back to the fact that their algorithm, the one they got scooped on,
Yeah.
turned out to be mostly classical.
Because at those higher temperatures,
Yeah,
the systems were behaving more classically, less quantum.
exactly. This is what people call dequantization.
Okay.
The idea that some systems might lose their quantum behavior at high temperatures
Right.
and their accidental discovery is a really clear example of that.
Wow. So they accidentally proved that dequantization is a real thing with real consequences.
Exactly, and it highlights this really important question
Yeah.
of where exactly is the line between the classical world and the quantum world.
Right.
It's a line we're still trying to figure out.
So this makes you wonder, right? Like, if entanglement is so fragile
Yeah,
at high temperatures,
yeah.
what does that mean for quantum computing in the future?
Right.
Is this like a big setback?
It definitely makes things more complex.
Yeah.
Entanglement is what we're hoping will make quantum computers
Right.
so much better than normal computers. And if you
Right.
need to keep them super cold
Yeah.
to keep entanglement working,
Yeah.
that's going to be a tough engineering challenge.
Yeah.
But I wouldn't say it's a game over.
So it's not like the end for quantum computing, but it means we need to get clever
Yeah.
about how we build these machines.
Exactly. And it makes finding quantum algorithms that have a clear advantage,
Uh-huh.
even at low temperatures where entanglement is stronger,
Right.
even more important.
Okay.
This discovery doesn't mean quantum computing is useless. It just means we need to be smarter about using its power.
Makes you think about how much we still don't know about this whole quantum world.
Yeah, it's true. And this is a great example
Yeah.
of how science often moves forward through these unexpected discoveries.
Right.
These computer scientists weren't even trying to make a physics breakthrough,
Yeah.
but their work ended up giving us a deeper understanding of how the quantum world works.
It shows that we need to be open
Yeah,
to new ways of looking at things.
for sure. Sometimes the biggest insights come from people
Yeah.
who come at a problem in a totally different way.
Right.
And who knows what other connections are out there waiting to be found?
Yeah.
What other crazy discoveries are waiting to be made
Right.
at the intersection of fields that seem totally separate?
That's what makes science so cool, right?
Totally.
This constant process of learning new things,
Yeah.
challenging what we thought we knew,
Uh-huh.
and getting a better and better understanding of how the universe works.
It really is amazing.
Well, we've reached the end of our deep dive into this wild discovery
Yeah.
of how heat can destroy entanglement.
Right.
But it leaves us with some questions.
For sure.
What else out there might affect entanglement?
Yeah.
What other surprises are hiding in the quantum world?
Right.
And what could those surprises mean for the future of technology and
Sure.
our understanding of the universe?
Totally.
Something to think about until next time.
Yeah, see you then.